Hi everyone. Um, what I have here in front of me is a little device using lead screws as my drive or my actuator. Um, and what this device is designed to do is have these 2 points right here and here actually actuate but travel in opposite directions, whether it's towards each other or away from each other. So that what that's going to do is it's going to create a parallel clamp is what it's going to do, or a gripper. A lot of the grippers that get designed work on a linkage system that are radial like this, and those are fantastic. Those are great. What a parallel gripper affords you is the target, or what you're trying to grip, doesn't have to be in the same exact location each time, whereas if you had radial fingers, the location's more important because the pickup point is specific to where that radius is going to close. Here they close parallel to each other, so you have the advantage of whatever your jaw assembly is going to look like on each side, whether there's geometry built into it to capture whatever it is that you're trying to pick up. So that's what this device is. It's a little parallel gripper, believe it or not. And like most of my videos, there's not a specific task that this design is built to do. It more encompasses like some of the maybe points that you'd want to add to maybe your design, so that for instance, if you wanted to use the lead screw, maybe there's some information in here that you could borrow from and apply that to your design. So like usual, I like to design from the motor output shaft out rather than in reverse, where I have a task and I design something to do, perform that task, and then work back to the motor in hopes that I have a location for it. I like to start at the beginning, and it's my motor. And like a lot of the other videos that you may have seen and hopefully have looked at some, it's a standard motor assembly. The motor has a certain footprint that it's going to sit in, and then I calculate in my mind in a sketch where that center line is going to be of the output shaft, and then I design from that point out. In this case, I have 2 lead screws with the Acme thread. There's another video prior to this one that describes the lead screw a little more in detail, but I'm using 2 lead screws parallel to each other, single drive, and secondary drive right here is geared so that when this rotates, these are going to rotate either clockwise and counterclockwise, or vice versa, depending on the rotation of the motor, of course, which causes these to rotate opposite each other. And how we actuate the gripper itself is I've fabricated these bushings right here that attach to each one of what my grippers are going to attach to. And one of these is a clearance hole that's relatively tight to this diameter, this overall diameter. In this case, it happens to be 3/8 of an inch. And the other one's threaded to accept the pitch of the Acme thread. And then it's just the opposite in this. If this one's threaded, this one would be threaded. If this one's clear, this one's clear, obviously. So as this rotates, it's no different than putting a screw onto a bolt. As you rotate it, the screw is going to travel down, and as you go in the opposite direction, it's going to travel down in the opposite direction also. So that's the theory behind this. As the rotations are opposite each other, it'll cause the threaded bushing on one side to travel down, and the other one opposite it on this side to travel down in the opposite direction. Then when you reverse the motor's direction, or rotational direction, that'll cause the jaws to close back up. So let's look at some of the construction of it. Some of the construction, pretty simple, right? I've located my center line of my output shaft, and I have to carry that center line right through anything that I'm attaching to that output shaft. We can't have misalignment, otherwise we'll have binding, correct? So I have my output shaft here, I have my first support plate here, and my outer support plate here. And what I've done, if you notice, I've chosen to use ball bearings instead of the bushings that you might have seen in some of my other videos. There's the difference right there, right? There's a bushing, and here's the ball bearing right there. I chose the ball bearings because they have an incredible radial strength. Like any pressure on these, the ball bearings are able to absorb that. And the only friction you really get, technically, I guess, from a ball bearing is the rolling friction of the balls. Here's a larger scale bearing that I pulled out just to kind of show the balls, how they rotate in there. So the real friction comes from the rolling friction, which is really minimal, especially in this application. But that's another video later on, bushings and bearings. But so that's what I've done with the bearings on each one of these plates. I fabricated these bushings through with Delrin. Again, one's a clearance hole, one's threaded to accept the thread, and then they pin to the shaft. The Acme threaded shaft is turned down to a 1/4 inch diameter on the ends. You can see right there, using a live center on the lathe just so I have concentricity right throughout the entire thing. Same goes on this end. This is all part of the Acme thread. It's all one shaft. And if you can see that, the diameter here has been turned down to accept the adapter for the output shaft on the motor. So one other point I'll point out to you right here is these bushings. If you notice, I have 2 screws in each face of the bushing, or the flange of the bushing. That's on both sides. The reason I did that is because there's going to be friction internally in these bushings, and I can't have too great of a press fit into here to keep them from being able to move as the rotation of the Acme thread is. So I had to retain them somehow, and by putting the flange on the bushing and then threading it into here, that retains that. If I made the bushings tight enough that they wouldn't move, it would collapse the ID, the inside diameter, whether it's the threaded one or the clearance bushing, and that would cause great friction that would be realized all the way back to the motor. So to eliminate that, I made them a light press fit and retained them with the screws in the flange, and I used, I believe, 632 screws to thread it into the jaw piece. So let's see what happens here. I'll actually plug this guy in. I'm partially prepared to do this, and you'll see the rotation of the motor and what happens with the Acme threads as we activate this. Alright, so here we go. So the intention is the device would be upright like this, and all the workings would be underneath, but I left it wide open so that you could actually see it function. So here we go. So as you can see, I'm rotating, the Acme threads are spinning, and it causes the jaws to open and close parallel to each other. So that's kind of neat, huh? You can see on this end here how the gears are meshed. As we rotate back and forth, you can see them opening and closing. One other feature I didn't point out yet was, you'll see this Delrin rod right here. turned down on both ends and supported on the two outboard supports. Believe it or not, that's turned down. And what that is these jaws just ride. There's a clearance hole in both of these. They just ride on this Delrin. Very smooth surface for it to operate. And what I'm trying to do with that, I guess I should say, is if there's any run out in the Acme threads, which there could be during fabrication, right? I don't want my parallel jaws doing this. So by putting that support right across the two jaw pieces, I think I've eliminated that. So, I mean, that's kind of it. Again, this device, and it's not specific to any challenge. It's more seeing the construction of it, and hopefully when you see it on the build demo table, it'll generate questions, and maybe you can apply something of this design into what you're trying to fabricate. Okay, I hope that helps.